Here we're going to look at multiplication rules for probability. And in order to do that, essentially what we are looking at is we are looking at what is in common between your events. Well, in order to do that, we have to determine if one event is going to influence the outcome of the other. This means, essentially, you have to look at your statement and determine if you have an independent statement or a dependent statement. Independent events or an independent statement is a statement where your two events are completely separate and there is nothing shared or influential between either event. Whereas dependent means that one of your events is dependent on the other event occurring or dependent on situations in your other event to occur. So the first thing that I want to do real quick is just make sure that we all have a firm understanding on what it means to be independent versus dependent. So I have a couple statements here. And what you have to do is you have to be able to determine in each statement if you are independent or dependent events. So my first one says, the color of a car driven by 3 randomly chosen classmates. So think about that statement very carefully. We are talking about, say, 3 students in a classroom and the color of cars that they drive. Now what you have to ask yourself is, does the color of a car depend on the classmate chosen, or does a classmate chosen depend on the color of car you're looking at? Well, no. They are completely opposite or separate. Not opposite. They are completely separate events. They have no influence on each other whatsoever. Therefore, that makes these independent. Now, my second one says a password must be 6 characters long with no repeated characters. Are the choices of consecutive characters independent or dependent? Well, the way you tell is very clear. Here, we have the word or the phrase no repeated. What that means is if I have to pick 6 characters or have something that is 6 characters long, if I choose, say, my first character to be the letter A, well then any of my additional remaining characters can no longer use the letter A. Since my second or next event in your statement is dependent on the results of the first event, these would be called dependent. Last are receiving a bill in Monday's mail and receiving a letter from your grandparents in Monday's mail independent or dependent. So what this is asking is, does the fact that you receive a bill on Monday have any influence on receiving a letter from your grandparents on Monday? Well, no. There is no influence in receiving bills versus receiving non-bills in the mail. You're just going to get in the mail what you get in the mail. Since none of those events are going to be influenced or depend on the previous events to occur, this would be considered independent. Now, the reason why being able to tell the difference in these statements is so important has to do with being able to determine which multiplication rule you will follow. So we have 2 different rules that we have to follow here. The first is the probability for independent events. The second is your probability for dependent events. So let's look at independent events. So when we're talking about independent events, again, you're talking about events that do not influence each other in any way. You are going to multiply those 2 probabilities together. So for example, given a fair die, so a fair die means that you have a dice that has a set of 1 to 6. and a deck of cards. So here, when we're talking about cards, we're talking about a standard 52 deck of cards. We want to find the probability of rolling a 3 and drawing an ace. So what we have to do here is first we have to find the probability that we're going to roll a 3. So in that case, to roll a 3 says I have one choice out of 6 total options. And then I need to look at the probability of finding an ace. So in this case, I have 4 aces out of my 52 cards. Now, if I look at this, the probability of rolling a dice and the probability of selecting a card are independent events. Okay, rolling a dice is going to have no effect on the card that I choose and select. So here, my probability that I roll a 3 and draw an ace, which, and right here is that big indicator that you are going to multiply, says I'm going to take my rolling, so 1 over 6, I'm going to multiply that by drawing my cards, 4 out of 52. And in this case, we're going to end up with 4 over 312. We're going to give ourselves a probability rounded to the millionth, so we're going to get 0.012821 is my probability. Okay. So again, the important takeaway there is that we have our equation right here, which says the probability that A and B occur is going to be multiplying the probability of A times the probability of B. Now for dependent events, we use your conditional, because a dependent event means that one of my events is dependent on the other event occurring. So we're still going to use my multiplication rule, but it's going to be slightly different. Instead of doing the probability of A times the probability of B, we would do the probability of A times the conditional probability that B occurs given A existed, or given the events of A. Excuse me. Alright, so let's look at a couple examples here so we can walk through and you can see how this is going to work. Okay? So we want to calculate the probability and we want to determine if it's independent or dependent. Okay? So here we have consider the spinner. And we want to find the probability of spinning an even number and a number less than 7. So the first thing we need to do is we need to look at the probability of spinning an even number. That's my first event. So here we would have 2, 4, 6, and 8. So here this would give me 4 choices out of my 8 total choices. The next thing we have to look at is we need to look at the probability of spinning a number less than 7. So here we have our 7, so we would have 6, 5, 4, 3, 2, and 1. So here this would be 6 out of 8. And so here we have to then also look at, does the probability of spinning an even number depend, or sorry, let me say that again. Does spinning a number less than 7 depend on our ability to spin an even number? Well, in that case, it would be no. Therefore, these would be considered to be independent events. So our overall probability of spinning an even and having x less than 7 is going to be my probability of even, so 4 times 8, times my probability of less than 7, 6 times 8, which is going to give me 24 over 64, which is the probability of 0.375. 0.5. Now in this case, this is a finite decimal, it ends, and so therefore we would only have to include the 3 digits we have. Alright, let's look at another one. Find the probability of choosing a heart and then an ace from a standard deck of cards with replacement. So with replacement says I'm going to choose a card, look at it, and then put it back. So here I need to do the probability that I'm going to choose a heart. That's my first probability. To do that says I have 13 hearts out of 52 cards. Then I have to look at the probability of choosing an ace. So my probability of choosing an ace, in this case I have 4 aces. Since I'm putting my card back after I choose it, I still have 52 cards to choose from. Okay? Because the act of putting the card back, that says these are independent events. Therefore, my probability of choosing a heart and then choosing an ace is going to be 13 over 52 times 4 over 52. This is going to give me 52 over 2704, which is going to give me a probability of 0.019231. Alright, let's look at another one here. Let's find the probability that from a standard deck of cards you're dealt 2 cards, the 9 of clubs and then another number card. So first I'm looking at the probability that I'm going to get the 9 of clubs. Well, the probability of that happening is 1 out of the 52 cards I have. Now, notice I don't have anywhere stated that I'm putting it back. Therefore, this one, my second, which would be the probability of choosing a number card, is going to be dependent on the fact that I've already picked a number card to begin with. So I only have 51 cards left. Now I have to look at choosing my number card. And so in this case, what I have to remember is that there are 40 number cards in a deck, but I've already chosen one, therefore this would be 39. Now the other way that we would write this piece in here is using that conditional. And the conditional would say that I want to choose a number card given that I've already chosen the 9 of clubs. Okay, so that is my conditional. Now with this, because I have my conditional piece here, this would be considered to be a dependent statement, which means the probability of choosing the 9 of clubs and another number is going to be the probability of choosing my 9 of clubs, so 1 over 52, times my conditional, 39 over 51. So this is going to give me the probability of 39 over 2652, which is a probability of 0.014706. Now we can also view these probabilities in the forms of tables. Okay? So the following tables show student demographics for a sociology club or class. So here we have males and females, and then we have different grade levels, freshman up to senior. First and foremost, we want to find the probability that a randomly selected student from the class is male. So we're looking at the probability of getting a male student. Well, in this case, I just simply have to look at my male column. So here, this is going to be the number of males over my total students. So here, I'm going to add 3 plus 4 plus 1, which is going to give me 8, over my total students, 31. So I just simply add all the numbers here in my chart. So my probability is going to be 0.258065. Now the second part says find the probability that 2 randomly selected students from the class are a female junior and a male sophomore. So the first thing I need to do is I need to find the probability of getting a female junior. So in this case, I want to look here at female juniors, and I have 3. So there's 3 female juniors out of 31 total. Now, nowhere do we say that the students then go back. So once that female has been selected, I now have 1 less student to choose from. So the probability of finding my male sophomore, given that I already chose your female junior, is going to be male sophomores, which is going to be 4 out of the 30 remaining students that were left. That makes this a dependent statement. Therefore, we are going to take that the probability of getting my female junior and a male sophomore is going to be 3 over 31 times 4 over 30. So this is going to give us 12 over 930, which is a probability of 0.012903. Alright, let's try one more. In a production process, a product is assembled by using 4 different independent parts, A, B, C, and D. In order for the product to operate properly, each part must be free of defects. The probabilities of the parts not being defective are given below, or given by, and we have them listed. What is the probability that all 4 parts are defective? Okay. So first we have to look at what is our events. So we have the probability of event A happening, and this is not defective. Therefore, our second is our complement, which would be that they are defective. Since we only have 2 choices here, you either work or you don't. So I have to look at the fact that I have first the probability of A was 0.9. Therefore, the probability that it is defective would be 1 minus 0.9, which is 0.1. I need to do the same for product B, which is 0.7. So the complement is going to be 1 minus that 0.7, which gives me 0.3. I have to do C, so 0.85, which means its complement, 1 minus 0.85, which gives you 0.15. And last, my product D, again 0.9. So its complement is the same as A, 1 minus 0.9, which equals 0.1. Okay? So what I have calculated here is we already knew the probabilities of not being defective. What we needed were the probabilities that they were defective. Okay? And the reason we need that comes back to the question that we were asked. What is the probability that all 4 parts will be defective? So, in order to do that, the probability that all 4 are defective is going to be the probability that I have complement of A and complement of B, the complement of C, and the complement of D. In this case, this is the same as doing the probability of my A complement times the probability of B complement times the probability of C complement times the probability of D complement. Since we already figured all of those out, we know that this is going to be 0.1 times 0.3 times 0.15 times 0.1. When you multiply all of those together, we end up with 0.00045, which means we have 0.045% chance that all 4 parts are defective. Okay. So there you have it. You have roughly 5 very different examples, all demonstrating the different rules for the multiplication rules of probability. Remember, the biggest thing you have to look for is your statement independent or dependent? And that is going to determine which type of probability you are going to use. So if you have any questions, please let me know. If you're having trouble figuring out if your problem is an independent or dependent problem, feel free to send those my direction. I'd love to try and help you out. Otherwise, I hope you enjoyed yourself, and I'll see you next time.